All right, so now I'm going to discuss what is known as Gaussian quadrature. And Gaussian quadrature is based on the following observation. Okay, so let me just recall Newton-Cotes quadrature rules. Okay, so if you're given quadrature points sort of normalized to the interval from 0 to 1, and they're distinct, okay, then you can construct an approximation to an integral in the following way. All right, so if you take an integral from 0 to 1 of f of x dx, right, then what you can do is you can replace f of x with its polynomial interpolant, which is constructed by sampling f at points c1 to cs. Okay, so this is approximately equal to the integral from 0 to 1 of the sum from I equals 1 to s of f evaluated at ci times the Lagrange polynomial Li of x, and then I integrate this. So I have a Lagrange polynomial Li of x, and it's defined in the following way. So I take the product of j not equal to I of x minus cj divided by ci minus cj. And the Lagrange polynomial has the following property, that it satisfies this Kronecker delta property. So if you take Li and you evaluate it at Cj, this gives you the Kronecker delta function delta ij, which is to say that it's 1 if I is equal to j, and then 0, I equals to j, and then 0 if I is not equal to j. Okay. All right, so that becomes, by reordering the sum and the integral, that becomes the sum from I equals 1 to s of basically the integral from 0 to 1 of Li of x dx, okay, multiplied into f at ci, and then we call these things bi, which are the quadrature weights. Okay. And it's easy to convince yourself that if f happened to be a polynomial of up to degree s minus 1, then this process of replacing the polynomial by its Newton interpolating polynomial on s points is exact. Okay, so recall that polynomial interpolation on s points is exact for functions f of x which are in the space of polynomials up to degree s minus 1 in x. All right, and so since this Newton-Cotes formula is obtained by taking the integral of f and replacing it the integral of its polynomial interpolant, if the polynomial interpolation is exact, that means that the Newton-Cotes formula is exact for this space of functions as well. So in particular, Newton-Cotes is exact if f of x is in the space of polynomials up to degree s minus 1. Okay, all right, so that's just a brief recap. So you can ask the following question, right? Can we choose the C1s to CS wisely such that Newton-Cotes is exact for higher degree polynomials. So because so far it's like when we've constructed Newton-Cotes formulas, this exactness property for polynomials up to degree s minus 1 is true independent of the choice of C1 to Cs, so long as they're in this interval and so long as they're distinct. Okay, so the question is, you have these s choices, if you will. It's like for the values, you can ask whether there is a you can do better than just exactness for polynomials up to degree s minus 1. So, in principle, with those s additional degrees of freedom, you might imagine that maybe you could conspire to construct a method which is exact for polynomials up to degree 2s minus 1, for example. So is there a way to do that? And that's really the subject of what's called Gaussian quadrature. And as we will see, this is intimately tied with the theory of orthogonal polynomials. Okay. So let's see what happens here. All right, so let's consider the following polynomial. Let's consider q of t, which is the product from I equals to 1 to s of, let's say q of x, okay, x minus ci. So this is just a polynomial which has c1 to cs as its roots, okay. Okay. All right, so this is a polynomial of degree s. So this is a polynomial of degree s in x. All right, so you can ask whether or not this polynomial is of degree s is orthogonal to all the lower degree polynomials, right? So one question is q of x orthogonal to lower degree polynomials? Okay, so this is going to impinge on the theory of what are called orthogonal polynomials. So what does it mean for q of x to be orthogonal to lower degree polynomials? So what it basically means is that you look at q of x and you take an inner product with some other polynomial of, say, a monomial. It's like of the form x to the k. Okay, and so you might ask, well, what is the inner product of functions as opposed to the usual inner product of vectors? Okay, so as is the case with vectors, what you have to do is you take the component-wise product of the two objects, and then you have to sum it over the indexing set. So since you have a continuous interval from 0 to 1, instead of taking a sum, you take an integral. And so what you would be looking at is something like the integral from 0 to 1 of q of x times x to the k, and you integrate it over x. Okay? So this is the inner product, if you will. It's like between these two functions. And so for it to be orthogonal, right, then you basically want that q of x, inner product of x to the k, is equal to 0, maybe for k equals to 0, all the way up to some m minus 1, which is less than s. Okay? All right, and so of course it's possible that it's orthogonal to nothing at all, in which case m would be 0. Okay. All right, so let's just assume that you have this kind of orthogonality property that q of x is orthogonal to maybe some set of low degree polynomials, and you'll see what happens when you apply the Newton-Cotes formula. It's like two polynomials of higher degree. Okay, so m is going to play a role here. So it tells you how many polynomials this thing is orthogonal up to, and the claim is that the more polynomials, it's like this specific polynomial, which is the product of monomials involving roots at the quadrature points. The more of these, the more this is orthogonal to lower degree polynomials, the better the quadrature rule is in some sense. Okay, at least in terms of exactness. So I'm going to consider a polynomial p of x, right, which is in the space of polynomials of degree s minus 1 plus m. Okay. All right, and let's see what happens. Okay. So I'm going to write p of x in the following way. So p of x is a polynomial of degree, it's like again s minus 1 plus m. So you can write p in the following way. There is a polynomial q, okay, which is a polynomial of degree s. Okay, so there's a sort of a polynomial, let's say s of x, which is a polynomial of up to degree m minus 1, and then there's a remainder term r of x, which is in the worst case a polynomial of up to degree s minus 1 of x. Okay, so what essentially I'm doing is that I'm doing synthetic division. It's like of p of x by I'm quotienting it by, it's like q of x, and then I have the it's like I have this factor here, which is a polynomial of degree up to m minus 1, and I have a remainder term, which in general is a polynomial of up to degree s minus 1. Okay, so let's see what happens. All right, so I'm going to evaluate the integral of this polynomial, say 0 to 1 of p of x dx, and I'm going to use this kind of representation of p of x as sq plus r. Okay, so this is the integral from 0 to 1 of s of x q of x dx, right, plus the integral from 0 to 1 of r of x dx. Okay, so let's see what happens here. So the first observation is this. This is, of course, nothing more than the inner product between s of x and q of x. Okay, but s of x is a polynomial degree up to m minus 1, and then by assumption, q of x is orthogonal to all polynomials of up to degree m minus 1. So this inner product here vanishes by orthogonality. Okay. Right, then you're just left with this term here. So that's the first observation, and then let's see what happens when we look at the quadrature rule. Okay, so the quadrature rule says that you have, it's like you have the sum from I equals 1 to s of p evaluated at ci times bi. Okay. All right, where bi is the Newton-Cotes weights, right? So bi is the integral from 0 to 1 of li of x dx. Okay, so let's see what happens. I'm going to rewrite p now again as sq plus r. So this is the sum from I equals 1 to s of s ci q ci plus r ci multiplied by bi. Okay, so now it's like if you look at this, you observe that q is being evaluated at ci's, but by construction, q has roots c1 to cs. So this term here vanishes. And so what you're left with is the sum from I equals 1 to s of bi r at ci. Okay? So putting everything together, what we have is the following, right? We have that the integral from 0 to 1 of p of x dx is equal to the integral from 0 to 1 of r of x dx. And we also have that the quadrature approximation, I equals 1 to s of p ci, I'll put a bi here, is equal to the sum from I equals 1 to s of bi r ci. Okay. So one final piece of the puzzle is that r is a polynomial degree s minus 1. So r of x is a polynomial degree s minus 1. Okay, but if you look at these two things, this is nothing more than the integral of a polynomial of degree s minus 1 up to degree s minus 1, and this is its Newton-Cotes quadrature approximation. And we already knew that Newton-Cotes is exact for polynomials up to degree s minus 1, so these two things are equal to each other. Okay, so the integral from 0 to 1 of p of x dx is equal to the integral from 0 to 1 of r of x dx, which is equal to its Newton-Cotes quadrature approximation. But this is equal to the quadrature approximation of the integral of p. Okay, so it has to be that everything is equal. And this implies then that if you choose sort of the C1s to Cs such that, okay, q of x, which is this product of factors, monomials, x minus ci, right? So if this thing is orthogonal to basically polynomials of up to degree m minus 1 of x, right, then the formula, the sort of this numerical quadrature formula, is exact for all polynomials p which are in polynomials of up to degree s minus 1 plus m on x. Okay, so you're always guaranteed to be exact for polynomials up to degree s minus 1, but if you've conspired to choose the CIs in such a way that when you take the product of these monomials, you get a polynomial which happens to be orthogonal to be the constants, the linears, the quadratics, and so on, then you end up getting a method which is exact not just for polynomials of degree up to s minus 1, but for higher degree polynomials as well. Okay, and then what you can see, it's like we'll talk about this later, is that in some sense the best you can hope for, it's like when you have a polynomial of degree s like this, is that it's orthogonal to all the lower degree polynomials. So it's orthogonal up to degree up to polynomials of degree s minus 1, which basically means that m here is s. And so in the best case situation, what this construction allows you to get is a quadrature rule which is exact for polynomials up to degree 2s minus 1. Okay, and so we will talk about how you go about constructing such orthogonal polynomials later on.